Okay, so in the previous lecture, we discussed the principle of momentum, the principle of impulse, the principle of average force, and the idea of how the same force can be distributed over different periods of time. And today, we are going to talk about billiards or snooker. So let's get started. We have two balls, purple and orange, 4 and 5. Orange ball comes, hits the purple one, and orange stops, purple moves. Let's look at that again. This is something that happens all the time if you play pool. And there's a reason why that happens. Okay. Why is it that when ball orange stops, the purple one starts moving? Well, turns out when we have a collision between two objects, there are two things that we have studied so far, which now we need to bring together. Okay. Momentum and kinetic energy. In a collision, momentum is conserved. We don't have an external force. These two bodies are part of the same system. So the momentum before the collision is the momentum after the collision. Now, collision forces, if we are looking at it as one system, are considered internal. Now we have different types of collision. We have collisions that we call elastic, collisions that we call inelastic, and collisions that we call completely inelastic. Okay. Now, when you think, how many people here have played billiard or snooker at some point in your life? Yeah. So this thing keeps doing ding, but I'm not actually seeing the. Okay, here we go. All right. When you play billiard and you get the white ball or you get one ball hitting another ball, there are multiple things that can happen, right? Option one, let's call white ball, colored ball. Okay, because we usually hit the white ball. We have multiple options. Option one, white ball stops, color moves. Option two, white moves, color moves, different V. Option three, white goes back, C moves. Option four, white and color move together. Any other options that I have forgotten? No?
The direction.
Directions could be different, but the movement and stopping, this is pretty much it, right? Okay. Now, turns out each one of these is because one of these, okay? Now, while momentum is conserved, kinetic energy is not always conserved, okay? So if we have an elastic collision, kinetic energy is conserved completely. Momentum conserved, kinetic energy conserved. If we have an inelastic collision, a bit of our kinetic energy is lost. Say, for example, as heat or as sound or as something. Or, crumpling or something, I don't know. And if we're looking at something completely inelastic, then after colliding together, the two objects actually stick together and move together as if they are a single object. Okay? Write that down, and then I'll go to the next slide, because we're going to keep referring to these over and over again. Okay. Let's look at one dimension. Total momentum before collision equals total momentum after collision. We have two bodies, M1, M2, white ball, colored ball, one hitting the other, with two different velocities, V1, V2. After they hit each other, they are still both moving, and they have V1F, V2F. ما شرط يكون نفس السرعة. How do we write that down? Well, P1I plus P2I equals P1F plus P2F. M1V1 plus M2V2 equals M1V1 plus M2V2. So far, so good? We sub in the values, we get the numbers. Everyone's happy. Okay. Let's take a look at another option. This sometimes happens. They stick to each other, and they move together as if they are one body. In this case, initially, my ball was coming with V1I, but my second ball did not have a velocity. It was stopping completely. And finally, they were both moving together at the same velocity. So what will it look like? Well, my initial momentum is simply because of the one that is moving, so M1 V1I. And my final velocity is the same for both of them, so M1 plus M2 multiplied by V. Okay. Let's consider them. If we consider them as one system, let's look at the velocity of the center of mass. We have an incoming projectile and a ball that is, so this is the incoming projectile, this is the stationary ball, and this is the center of mass. Here's what happens. Look at what happens to the center of mass, velocity of center of mass. The center of mass of two bodies moves at the same velocity, both before and after two bodies stick together. Now, I know I'm giving you a lot of information, but we'll do a lot of examples on them in a bit. Just bear with me. Let's do a sample problem to bring everything we said into perspective. So sometimes in physics, we have experiments for which we do not have one equation that just makes it work. We need to figure it out. So we break it up into steps and do it individually. We take the example of what we call the ballistic problem. People wanted to measure the speed of a bullet, but way before the electronic timing devices were made. Now, that was a problem because bullets were really, really fast, and they did not have something fast enough to, measure the speed of it. So they had to figure out a different way to measure the velocity of a bullet. So they were like, okay, fine, fine, don't panic, don't panic. I will take a bullet that has a mass of 9.5 grams, shoot it at a big block of wood that weighs 5.4 kilograms of mass, and that is hanging. Now, what happens when the bullet hits the wood?
The wood will move.
The wood would move, right? The bullet would go inside the wood, and they would both move, and it would go up. Now, from conservation of energy, we know that the amount of kinetic energy that this bullet had would end up raising this block of wood by some height, h. It will give it potential energy, gravitational potential energy, mgh. And since it's moving, it will eventually stop moving and all the kinetic energy would have gone to mgh. So if we measure h, we can know the amount of energy and we can know what was the initial velocity. So they measured h and it was 6.3 centimeters. So now they were like, okay, what's the speed of the bullet? We start with momentum. My momentum before the collision is equal to my momentum after the collision. So before the collision, I had m bullet, v bullet, plus m wood, v wood, which is, this is 0. So we just have m bullet, v bullet. After would be, they're both moving together. So m plus m, v total. Now, that is one equation, right? But we don't know what this v is, and we don't know what this v is. We only have the m's. So that's not enough to find the answer out. But we have another piece of information. We know that the initial kinetic energy is equal to the final potential energy. If we rearrange this, okay, we can find what the initial velocity was. And we can find that it was 630 meters per second. So what did we do here? We did it in multiple steps. Step 1, momentum is conserved. Step 2, energy is conserved. Step 3, find velocity at collision by conservation of energy, then use that in conservation of momentum to get VI. Any questions? No? All clear?
Doctor, so the only collision the kinetic energy is not conserved is inelastic collision?
In elastic, it is completely conserved. In non-elastic, it is partially conserved. And in completely inelastic, it is not conserved at all. So here we are assuming that the energy is conserved. We're not losing it to heat or anything. Now, in reality, that's not very accurate because when a bullet is going to go inside the wood, there will be friction and heat. So this would be a partially inelastic or completely inelastic collision.
So the question mentioned that this is elastic?
No. So the question simply tells you what it is, and then it tells you, okay, figure it out. So what we do here is, first we say, okay, momentum is conserved no matter what. So we do the conservation of momentum. Then we say, okay, when the bullet and the block swing up, our mechanical energy, our total energy is conserved. Okay, so we're not assuming kinetic energy here. We're not saying, okay, we're not saying that the initial kinetic energy is equal to the final kinetic energy. No, we're saying that the kinetic energy is conserved, so it's equally actually to the end to potential energy. So we did not assume here this is elastic. Okay, we'll do elastic collisions in the next slide actually. Okay. Okay. Let's look at elastic collisions. This is one of those chapters where things are confusing until we cover everything, and then we're like, okay, so this is different to this, different to this, different to that. All right. If we have an elastic collision, a properly elastic collision, the total kinetic energy before the collision is equal to the total kinetic energy after the collision. Now be very careful. Here we are talking about conservation of kinetic energy in elastic collisions. But at all times we have conservation of total energy. So in the bullet example, we were not conserving kinetic energy, but we were conserving total energy. Okay, so in an elastic collision, the kinetic energy of each body may change, but the total energy, kinetic energy of the system does not change. Like what? Say, for example, we have a moving target. We have a moving target. M1v1, M2v2, M1v1, M2v2. This is the momentum. And my kinetic energy will be half mv squared, half mv squared, half mv squared, half mv squared with different subscripts. I get a whole bunch of complicated equations, which I'm going to tell you to ignore, because in a bit I'm going to tell you exactly how to do it. Okay. You had a whole bunch of equations here, right? Do you need to memorize these? Yes, no, maybe?
No.
No need to memorize these. What do? You simply stick to the principle. Pi equals Pf, and if elastic, Kei equals Kef. And then you write it down. M1v1 plus M2v2 equals M1vf plus M2vf2. And you move it around. Okay. If you try to memorize these, you will end up with very, very complicated formulae in your head, which confuse you. Now let's look at a stationary target. Both of them initially moved, both of them were finally moving, just different velocities. I'm going to ignore all of these and just come here. Let's take the example of an elastic collision where both, like billiard balls, where both of the objects are the same size, same mass. What happens if M1 equals M2 when they hit each other? If M1 equals M2, V1F, so I'm going to write the full formula here without working through them. I'm going to copy these formula here, but you don't need to memorize them. Okay. My V1F is going to be 0. My V2F is going to be the same as V1I. And that makes sense because they are the same mass. So if one of them loses its momentum completely and its energy completely, the other one will gain the exact same amount of momentum and exact same amount of kinetic energy. So it would have the exact same velocity. Does this make sense?
Yes.
What if we have a very tiny thing hitting a very, very big thing? What happens? You have the formula up in the corner. Can you think of it? What happens if a tiny, tiny thing hits a very big thing? No.
إنه نيترال بالأرجع.
Okay, that's one option.
The tiny thing will reverse its direction.
Okay, that's another option. Now, we know from whenever we are fighting or watching a fight, الحوش, أنه if a tiny guy hits the big guy, that's a really, really bad idea. He's going to end up going backwards. Okay. So if I have a massive target, that means the mass of the big ball, M2, is way more than M1. So I can approximate my equations. Yeah. If M2 is way more than M1, okay, then M1 minus M2 is approximately what? Just minus M2. صح? If I have M1 equals 1 kilogram, M2 equals 1,000 kilogram. What is M1 minus M2? Minus 999 kilograms, which is approximately simply minus M2. What is M1 plus M2? Again, M1 is almost nothing here, so it's still approximately only M2. So my small object is going to go in reverse at negative the speed it came at, approximately. And the big thing will go forward at this rate. So if we're talking 1 kilogram and 1,000 kilograms, you would end up at a velocity of 2 divided by 1,000. So this is around 0.002 VI. So it will move, but the movement's velocity will be very, very tiny, which again makes sense. Small guy pushing big guy isn't going to move much. What if it's the other way around? What if it's a really big ball hitting a tiny ball? What happens then? Have you ever been walking on an escalator ولا واقف في مقصف المدرسة ويجي لك واحد حجمه ما شاء الله XX large من ورا ويدعمك? What happens to you?
The tiny ball and the big ball will move to the same direction.
Okay, they will move to the same direction. What about their velocities? What happens when a big guy suddenly bumps into you? What happens to you?
Make it fly.
your velocity will be increased.
كأن تجيك دفرة صح؟ احتمال هو ما دافرنك. It was a simple bump. It was not a push. But to your body, it feels like a push. You go forward very quickly, right? Turns out there's a reason for this. The big guy is going to just keep on going at the same velocity. ولا كأنه سوى شيء ولا كأنه صار شيء. But the small guy is going to end up moving at twice the velocity of the big guy. So if this guy was coming at 10 meters per second, okay, then after the collision, this guy would still keep moving at 10 meters per second ولا كأنه شيء صار يا جبل ما يهزك ريح. But this guy will end up moving at twice that, 20 meters per second. Okay? Any questions so far? Okay, let's do some PIQs to see if we have understood these concepts or not. Ball 1 hits stationary ball 2 in a one-dimensional elastic collision. The initial momentum of ball 1 is P1I. Final momentum of ball 2 is P2F. And they are both shown on the graph below. P1I is 4, P2F is 5. What is the magnitude of the x component of P1F? Now, this is not an easy problem. It's slightly confusing. So, as we have established over and over again, the best way to learn is to teach. So let's go into our groups. And
Just show us the question to take a picture of it.
yeah, I'll do that. Give me a second. Here we go.
Done.
Okay, everyone ready? I will also see if I can put it here. Nope, not possible. Nevertheless. Okay. Let's do this. Okay. So let's see. We have some people choosing 1, couple people choosing 0 and 2, but mostly people choosing 1. Let's see if 1 is correct. We want to find P1Fx. So let's start. Ball 1 hits a stationary ball 2. So we know we have a P1I. So we have 1 and we have 2. P2I is equal to 0 since velocity is 0, stationary. The initial momentum of ball 1 is P1I, which is equal to 4. And the final momentum of ball 2, P2F, is equal to 5. What is the magnitude of the x component of P1F? 0, 1, 2, 3, or none of the above answers is correct. Well, we know that Pi equals Pf. P1I, now apparently there's an x-axis and a y-axis. Okay, we want to know what is P1F. So P1I plus P2I equals P1F plus P2F. P1I is 4, P2I is 0, P1F is we don't know, P2F is 5, which means that P1F is equal to 4 minus 5, which is equal to minus 1. Magnitude of P1F is equal to 1. Well done to those who got it. Let's try another one. A big ball, mass m, equals 10 masses, 10m. Strikes a small ball, mass m, at rest. Could the following occur? The big ball comes to a complete stop, and the small ball moves with speed 10v. So I'll do this again. Wait. Yeah. So assuming it's an elastic collision, can this ball, which has a velocity of 10 mv, hit a stationary ball with just mass m, stop completely, and ball m moves at 10v? Yes. No, because it would violate momentum conservation. No, because it would violate conservation of energy. And this is an interesting question, which always let's see what you think. I'll give you 2 minutes, or 3 minutes actually, to think about it. If there's nothing else we do today, we need to have we need to know how to do this. Initially, you have 10m and velocity v, and finally, you have 1m and velocity 10v. Is that possible or not possible? Consider both the conservation of momentum and the conservation of energy and see if it works out. Type your answer in the chat box or answer it in the poll. I prefer if you answer it in the poll if you're able to. Okay, one more minute. Okay. Let's see. We have 37 people who said yes, 6 people who said no because it violates conservation of momentum, 7 people said no because it violates conservation of energy, and we have 1, 2, 3, 4 more people, so 41 people in total who said yes, this is possible. Let's take a look. First thing first, momentum. Someone do it with me. What is the momentum before collision? Oops. 10m v plus m v is 0 is equal to momentum afterwards 10m v is 0 plus m 10v. So we have 10 mv equals 10 mv. Momentum is conserved. Good. Anyone has a problem with conservation of momentum? Okay, this is good. Let's look at energy. What types of energy do we have here? Anyone?
Kinetic energy.
Kinetic energy. Do you have anything other than kinetic energy? So initially I have half 10 mv squared. Finally, I will have half m 10v squared. Okay, so this is 10 over 2v squared, which is 5v squared. And this side, we have 100, 10 squared is 100, 100 mv squared over 2, which is 50 mv squared. Anyone sees a problem here?
They are not equal.
Not only are they not equal, the energy seems to have suddenly increased. Yeah. Now, if we had started with 50 and ended up with 5 mv squared, نقول okay, friction, we lost energy. ما مشكلة, inelastic collision. Sound, when they hit each other, we lost energy due to sound. We lost energy due to elastic deformation. We lost energy somehow. That is why my thingy is, my energy is less. صح? That's okay. We can find a solution. ممكن نطلع له عذر. But here, we seem to have started with 5 and ended up with 50. So that is a problem, right? This means this thing cannot happen because it would violate the conservation of energy. It would, if this happens, momentum is conserved, that's fine, but it would also require us to increase the energy by tenfold out of nowhere. So this is not possible. Now, what happens if this collision is actually in 2 dimensions, not 1 dimension? Say, for example, we have this ball here, and something comes, hits it. One goes upright, one goes bottom right. How do we do the calculation here?
By components?
Yep, by components. Each one of these have their components. First thing first, we have kinetic energy, which is amazing because we don't need components in it. Okay, because it's not a vector, it's a scalar. So half m1 v1 squared initially equals half m1 v1 f squared plus half m2 v2 f squared. Lovely. No need for components. Now we come to momentum. We need to do it in components. Initially, we have m1 v1, which is purely in x direction. This would equal to m1 v1f cosine and m2 v2f cosine. Only the x components. Same thing in the y-axis, but we have a minus here because it's now in the down direction. Is this clear? Anyone confused by this? Okay. If this is clear, let us how much time do we have left? Not much. Let's do this sample problem in your book. In this problem, we have a block coming into a line of 2 blocks that are not moving at a velocity of 10 meters per second. It hits block 2, and then block 2 hits block 3. Okay, like dominoes. 1 hits 2, 2 hits 3. M3 is 6 kilograms. And what we know is, after the final collision, بعد ما كل الخبصة تخلص, block 2 is not moving. Block 3 is moving at 5 meters per second. And we're told to assume the collisions are elastic. We need to find the rest of the information. So here's what we know. M1 hits M2, M2 hits M3, and M2 stops. V1I is 10 meters per second, M3 is 6 kilograms, and V3F is 5 meters per second. What do we do? Well, we have a system of equations. This is what happens. Hit, go back, go forward, hit, stop, go forward. So we do it in parts. First, I will actually ignore M1. I will go to 2 and 3 أول شيء. وبعدين برجع. I know V2I, I don't know, but I know V2F is 0 because it stops. I know V3I is 0 and V3F is 5. And I know its mass. Now, by conservation of momentum, I can relate the final velocity of 2 to the initial velocity of 2. That gives me M2 is equal to M3, 6 kilograms. I then plug that back in, and I get that the initial velocity of V2 is 5 meters per second. Now this might be confusing, so let's do it on a whiteboard properly. What do we have here? We have Pi equals Pf, M2 V2I plus M3 V3I equals M2 V2F plus M3 V3F. Let's substitute. What was V3I? 0. What is V2F? 0. So we end up with M2 V2I equals M3 V3F. This M3 is 6, V3F is 5, so this is 30. Okay. But we still don't know M2 V2I. Not good enough. We need one more equation. What other equation can we use?
Critical energy.
We can use kinetic energy indeed. Let's try kinetic energy. Half m2 v2I squared plus half m3 v3I squared equals half m2 vf squared plus half m3 v3f squared. This is 0, this is 0, but we still have a problem. We still have two unknowns, m2 and v2. Not good enough. We need to find another solution. We can bring it from the first collision. In the first collision, we said m1 hits m2. We know v1I equals 10 meters per second. So in the first collision, we know m1 vi plus m2 v2I equals m1 v1f plus m2 v2f. v2 initial is 0. We don't know anything else. Do we know anything else? We don't. Do we know anything else?
We can use the first two equations we have written.
Can you use the first two?
Yeah, the first two equations you write down.
Equation 1 and equation 2?
Yes.
Okay. Walk me through it.
So from the first equation, we know that M2 is equals to 30 divided by V2 initial. Then we substitute the value of M2 in the second equation. We can find the V2 initial.
Let's try it
And we
out.
already know M3 and V3F.
Good. So half 30 divided by V2I squared equals half. What is this? M3, we know it's 6. V3F, we know it's 5. Squared. كده?
No, the first side is supposed to be 30 divided by V2I multiplied by V2I squared. So.
Ah, yes.
V2I squared.
V2I squared. Wouldn't that cancel all our V2I's though? No, we don't have a square here. My bad.
Yeah.
Good. So we end up with 30 V2I over 2 equals 5 squared is 25 times 6 is 150 divided by 2, it's 75. Which gives me my V2I to be equal to 5 meters per second. Excellent. not only an excellent, well done job, we have actually, you have, not we, you have actually done it in a way differently to the book. If you look at the solution of the book and the solution of the slides, it has done it differently. It uses V1 as well, but you did not. You just used conservation of kinetic energy and momentum to get the exact same answer. V2I is equal to 5 meters per second. Very well done. Okay, we're running out of time. It's 12:25, so the lecture time is over. وأعرف إنه شهر رمضان وصايمين وتعبانين. So what I will do is, I will post these 3 slides. Okay. Actually, not this one. I'll post this one and this one with the lecture slides on Moodle. Try to read this question, number 71 from the book. Try to read it, do it on your own, then look at the solution that I post. Okay?
Okay.
Any other questions?